Welcome back to another day. Math 365 PDE. And so I'd like to pick up right where we left off. So we want to, as promised, study this wave equation in two spatial dimensions instead of one spatial dimension. So instead of the vibrating string, we can look now at like the vibrating drumhead. So we'll talk about that, and that wave equation now looks like two time derivatives of u minus propagation speed squared times the Laplacian of u equals 0, whereas before this was just two partials with respect to x. Remember, Laplacian u is that operator right there. And so I reminded you to remember the form of the Laplacian in so-called polar coordinates. You requested not to see a derivation of this. Totally fine with me. We put one online though. Welcome, coming in. And I'll write down the formula here. So the polar coordinate version of Laplacian is like two derivatives with respect to r. One derivative with respect to r divided by r. And then 1 over r squared d theta squared. I will speak a little bit about coordinate changes today. So I won't derive this formula, but I'll speak a little bit about polar coordinates, right? So what are they? So say you've got a change of coordinates function. So this may be familiar from vector calculus, right? And this is r cosine theta, r sine theta. I think that coordinate changes philosophically are kind of hard to understand. And that's part of the reason for that is the classical way we use notation. So you're more like to just see x equals r cosine theta, y equals r sine theta, and that's called the coordinate change. But more properly, the coordinate change is a function from one domain to another domain. And so G is like is what we call a diffeomorphism, or at least it should be. So I hate to throw around words, but diffeomorphism, what should that mean? Morph, change, you're changing one domain into another one, changing the coordinates, and you're doing it in a matter that is differentiable with differentiable inverse. So that's maybe explains the terminology and what domain to what other domain. So that's kind of the issue, because polar coordinates has a few problems, but let's look at, this is something that goes from r theta space into xy space. So I think we should have something like, I'll write theta on the x-axis even though it's the second variable. So we have something like we want a domain, so we want an open set. So maybe we want r bigger than 0, and maybe we want 0 less than theta less than 2 pi. And if you graph this, you kind of get this rectangle here. It's an infinite rectangle. Really, it's kind of like an infinite cylinder, because if you include the endpoints, then any function that you define on this space for r and theta to have the meanings you want them to, you would need like the value at theta equals 0 to be equal to the value at theta equals 2 pi, which is the same thing as sort of like closing up the rectangle into a cylinder. And so where do these coordinates go? So they go into xy space. And except we're missing r equals 0, so we're kind of missing this point. And I guess we are missing theta equals 0. So I guess we're actually kind of missing this whole part of the plane. So in terms of like one domain to another, the polar coordinates don't quite hit the entire plane. But apart from that issue, from this domain to that domain, then it does become true that this function g is differentiable. You can write down its derivative. It has differentiable inverse, and it is invertible on this domain the way we've got it. If you included the endpoints here, then you'd see that it was not invertible. And if you want to convert like some equation to another coordinate frame, then what are you doing? You kind of have to figure out how to write like dy and dx, like in terms of the other variable. So yeah, it's definitely all the chain rule, and you can like reason it out from the chain rule. I'll just kind of draw a little picture, and let's say that you've got some setup here. So like here's your angle theta, there's your angle r. Like even though you're kind of going from rectangular space from a rectangular space here to a rectangular space there with this region transformed according to that formula, it's still quite convenient to write down, you know, r and theta in this way, respecting what they look like from the formula. Even though more properly we're sort of translating from this space to that one. And so where are the derivatives in this picture? So I think that like they're basically tangent vectors. So this is sort of like d theta. And if you think about it, if you've got circle of radius r, your angular variable stays at 2 pi. So, but the circumference of the circle is like 2 pi r. So I feel like your angular derivative is going to have something like length r in order to, you have to be going fast at larger radii to cover the entire circle in angular parameter 2 pi. Of course, r, what happens as r increases, what does the derivative vector look like? Well, just going straight out. So that's kind of what dr looks like. And so I'm taking these derivatives as I'm like moving along theta, as I'm moving along r. So what do dx and dy look like? Of course, dy is just straight up, and dx is just straight that way. And if you're wanting to convert this equation into that one, like one way you can do it is you can say, what is dx, like in terms of dr and d theta? You can actually kind of look at this picture and use linear algebra and try to figure it out. You're not going to get much traction just looking at the picture, but there is a linear transformation that changes dx dy into dr d theta. What is that linear transformation? Well, it's going to be like the derivative of your coordinate change. Of course, here you've got a coordinate change from r theta to xy, so you should expect that dg will tell you how to convert a vector like dr into dx and dy. And what do I mean by this? And literally what I mean is if you calculate dg and plug in 1, 0, then the output will be AB. So 1, 0 is like your first coordinate. So that's like traveling along R. That's like giving you dr. And when you plug that in, you'll get the coefficients that you need to put in front of dx and dy. Strictly speaking, from a linear algebra standpoint, the derivative of g is a map from like the tangent space at a point to the tangent space at a point. The way you turn it into a matrix is you identify dr with 1, 0 and d theta with 0, 1. You identify dx with 1, 0 and dy with 0, 1. And under that identification, the matrix for the linear transformation will be the usual derivative matrix. And to be clear, you can totally write that out. The columns are what? Cosine theta, sine theta, the minus r sine theta, r cosine theta. If you wanted to write x in terms of dr, you would invert this matrix. You would invert this matrix and plug in 1, 0, and then this would give you the coefficients that go in front of dr and d theta in order to write, d dx equals constant times ddr plus constant times d theta. And I encourage you to actually check that out. It's a cool use of linear algebra. So if you do that, if you then do that to find formulas for dx and dy, you can just plug them in, right? You can just take dx squared of u plus dy squared of u, and this will pop out automatically. And I know you said you didn't want that derivation, so I won't give it to you, but I couldn't help myself a little bit to give some perspective on coordinates and the coordinate change, because I just think it's so easy to lose perspective or misunderstand at the undergraduate level. So when you're talking about the difference between this operator ddx and this operator ddr, what are you doing? You're basically writing this vector, in terms of that one and that one. So you're expecting to get something like ddx equals ddr, and then what do you have to subtract from that? You have to subtract some multiple of theta. Theta has length r, so it makes sense that you're, dividing by r. So this totally makes sense to me, that kind of dividing by r squared to make up the r squared in d theta. This one makes a little bit less sense, but whatever, we all do the calculation and that's what we get. Okay, fine. And so this is a wave equation that you can derive using the same method that we derived for just ddx squared. But let us not go through that again. It's quite intuitive that you'd add that extra term to add an extra spatial variable. So let's take this for granted, that this is our new wave equation. And now function u is u, t, x, y, or in polar coordinates, it would be u, t, r, theta, polar spatial coordinates. And this still represents the displacement from, bless you, this represents the displacement, the vertical displacement of the drumhead. So you can kind of imagine, a circular drumhead of radius 1 in the plane. And then you could imagine solving this equation with a boundary condition given by, when you plug in r equals 1, you should get 0 because there's always going to be 0 displacement. It's just a planar version of the drumhead. In real life, of course, this drumhead is sitting on a drum with an echo chamber behind it, but the model is a 2D model because you're just measuring the vibration of that film. And so then it would make sense to use polar coordinates for a situation like this. And yeah, you can solve this equation in complete generality according to its initial conditions. There's kind of a reduction method that takes you back once again to D'Alembert's equation. We're not going to do that today. We're going to focus on the harmonics today, which means we're going to focus on a separation of variables technique. So this technique is not very good in general. It only works in very special cases because the variables, well, I guess in a normal day I would shut the door got some noise in the classroom, but following procedures, I'll keep the door open. Okay, right, so what was I saying? Yeah, for separation of variables, the variables really do need to be independent. So you can really separate variables on domains that look rectangular and not on other domains. Because if you take a non-rectangular domain, there will be a relation between the two variables that determines the contour or the boundary of that domain, and you can't really separate those variables. So separation of variables is not just an issue of function of one variable times function of another one. The domain has to be separated too. You can see practical applications of that in statistics. It's like for multivariable statistics, two events are not independent just if you can separate them out as one times the other, but it also has to be on a square domain. And so this is not a square domain, but the point is it is a square domain in polar coordinates, and that's what makes separation of variable a rectangular domain. And that's what makes this separation of variable technique work. We also have to be a little bit careful about this issue of r equals 0. And we'll confront that as we go. So what happens? So what happens? Let us write u, like before, equals v times phi. V is a function of t, and phi is now a function of the space variables. And let's go ahead and assume that we've switched to polar coordinates. So we're already in polar coordinates. So I don't want to start with rectangular coordinates and then introduce new variables for these functions to represent them, under the coordinate change. Let's assume that we're already, written in polar coordinates. And in your mind, you're thinking about this unit circular domain. And we're going to separate variables twice. So we want to do like a spatial separation of variables. So you want to write like phi equals what? Let's take some function of r times some function of omega. So like h of r times omega of theta. And in a similar manner to how we derived things last time, the corresponding problem that you kind of get is this eigenvalue problem for the space variable. So you get this problem, Laplacian of phi equals negative lambda times phi. This is the Helmholtz equation, so I mentioned it last time, and I derived it in the one spatial variable case. And I mentioned that the very same derivation gives you this setup in two space derivatives. So kind of the point of this class is going to be trying to solve this eigenvalue equation, this Helmholtz equation. And then subsequent to doing that, you can kind of just go back and plug VH omega kind of back into this equation, and then you'll find a product solution in terms of V and H and omega. But for us, the difficult part is going to be solving this equation, and for that reason, I'm going to focus on it today. So let's try to do that. And let's just proceed in a manner completely analogous to last time. let's do this separation of variables technique, which is really just plug in this product formula into the equation and try to separate the variables. So let us do it. And we've got this formula for the Laplacian. So I'm going to take h times omega, and maybe you'll permit me not to like write, maybe to do a little less writing. So if I apply the Laplacian to h omega, I can do it piece by piece. So what's going to happen when I take d squared dr squared to that function, right? Because this is the function of r, it turns into h double prime omega, and then I add to it 1 over r times h prime omega, right? And then I add to it 1 over r squared. And now it's d theta squared, so now this becomes h omega double prime. And I'm using this compact notation, which I hope isn't too confusing, but do remember that these primes are honest to goodness single variable calculus derivatives. H is a function of r, omega is a function of theta. These are honest to goodness partial derivatives, but the partial derivative of the two variable function turns into the single derivative of the one variable function, times the other one held constant. If you do all the mathematics, that's definitely how it works out. So we've applied this, we've got the left-hand side, and now this is supposed to be equal to some constant. Do I want to already introduce? Yeah, so like we'll just keep calling the constant minus lambda times phi, which is h omega. So now separate the variables, so divide both sides. And also, well, okay, let's just do that for now. So h double prime over h. So since you're dividing by phi, you've got this implicit assumption that phi has to be non-zero on the region where you're making this separation. Yeah, that's exactly right. The comment was, and then you'll need to multiply by r squared to make this work out. And so we're not quite separated here, but finally we end up with and to finish the separation, we'll just sort of switch these two terms. So minus omega double prime over omega, and then plus r squared times lambda.
Would there be an r squared in the first term?
Yes. Thank you. All right, cool. And so like before, you've got this setup now where this is a function of theta, that's a function of r, and theta and r are independent of each other. And so therefore, each side of the equation must be equal to the same constant. I'll put up the equation we're currently working on. And so you can call this constant For now, I'll call it K naught. So let's look at just this omega term first. And similar reasoning to last time, multiply both sides by W, write it as something equal to 0, multiply by W and integrate, or in the complex case, multiply by W bar and integrate. So similar argument from last time tells you that actually K naught has to be positive. So lambda is from this Helmholtz equation, but the separation of spatial variables, since we're kind of doing it twice, introduces this new constant. And this new constant is really the analog of what we were looking at last time, at least initially. And so let's write K naught equal to K squared. Since it's a positive number, it has a square root, no problem. And then you want to solve this equation, which is like omega double prime plus K squared. Omega equals 0. And then from ODE theory, you can say, well, let's write down the characteristic polynomial. That's y squared plus K squared equals 0, and the roots of the characteristic polynomial give you your independent solutions in terms of like e to the tr. So you get these two independent solutions, like e to the I time, well, maybe times k times t, and you get e to the negative I kt as your set of independent solutions in this case. And so that tells you that actually, what do I want to keep? That tells you that actually omega is like some constant, you know, maybe ak e to the I kt plus some other constant e to the minus I kt. So choosing bk equals 0 and ak equals 1 for the moment, or in other words, focusing on this solution for the moment, we can make some observations. So this function phi, it's written in polar coordinates, and it has to be like a C2 function. So first, just by virtue of being written in polar coordinates, we make the requirement that omega is 2 pi periodic. And I don't think that's unreasonable. I mean, this is sort of a consequence of what I talked about at the beginning of class, where polar coordinates really kind of aren't good, except on this small rectangular. And then as you're making your choice of phase, as theta increases, you kind of keep going around the cylinder, if you like. It's really not a boundary condition because, I mean, it kind of is, like in a sense, but if you remember, like our domain is really the interior of this circle. And so what I'm just saying is, like, if you want to treat omega as like a function defined on R, then it has to be periodic, or else it wouldn't be defined on the circle. So it's really a condition of making omega well-defined. You can think about it that way. And this has a consequence for this constant k, because if you look at, so I'll keep that up here. Wait, which one? No, I'll keep this up here. If you look at, say, e to the I k theta, and this needs to be, like taking this for omega. You could take lots of things for omega, but let's take this for omega. And then this has to be equal to e to the plug in theta plus 2 pi. So you can kind of deduce here, right, that e to the I 2 pi k has to be equal to 1. Remember, e to the I theta is cosine theta plus I sine theta. And from that, you deduce that k has to be an integer because you must be a multiple of 2 pi in order for that to happen. So this constant can't be anything, it has to be an integer. And now that actually lets you simplify your formula for omega because you don't need k and it's negative if you're just letting k range through the integers. So you can now make the general sort of declaration that omega equals e to the I k theta with like theta inside the integers and maybe multiply it by some constant. A different constant than that one perhaps. But this now becomes your general form of the solution.
What about the negative case? Or are we just not?
The negative case is in there. It's allowed to be an integer. It's okay. Is integer. Yeah, yeah. I mean, omega can be linear combinations of these solutions, but maybe I'll just write it like this. Like if you just say that this collection is a linearly independent set of solutions somehow. Okay. So this, I mean, this is a method that's quite similar to last time. So in a way that's quite straightforward. But now we want to work on the like other side of the equation. So taking again this eigenvalue equation and then taking in our knowledge that you know, let's take omega to be one of these e to the I k thetas. You could multiply it by a constant, but it'll drop out of the equation. So we'll just keep it as omega equals e to the I k theta for some integer theta. And actually, since there's now this parameter k, which has to be an integer, I'll just call that omega k. And so therefore, I'll say solution phi k is now some function hk times omega k. Now that I know that I'm going to get one for each integer, I should identify a particular hk for each integer. And I know that omega double prime over omega, it's equal to this constant k squared. So let's substitute that in for what it's equal to. And these just become HKs. So not repeating the full derivation again, but if you substitute this in to that equation and then separate the variables and write it out, then this is now what you get, and you can now rewrite this as what? Just bringing everything to the other side. You get r squared hk double prime plus r hk prime plus r squared lambda minus k squared hk equal to 0. Just bringing that to the other side and multiplying through by hk, right? So that's clear. And this equation is the one that kind of has a special name. So if lambda equals 1, this is Bessel's equation. So this is the so-called Bessel's equation from other contexts that you may have seen. It just requires lambda equal to 1. The fact that there is like a constant here doesn't really bother us. We'll do a substitution and fix that right up, no problem. But I actually want to speak first about what? So lambda is the eigenvalue here. So back when we only had one space variable, we could kind of do an argument to show that lambda had to be positive. Since we're working with this more complex equation, there's no argument with integration that's going to tell you that lambda has to be positive. In fact, it doesn't have to be. So lambda could be 0, it could be positive, or it could be negative. And either of those three cases does change the qualitative character of the solutions that you get to that equation. So this equation is kind of hard to solve. So we should break it up into 3 parts. Yeah. Why is there an r squared here?
Yeah.
Because we multiplied by r squared through earlier too.
Oh, these are all 1 over r.
So yeah, when we were separating the variables, we had to multiply through by r squared to get a cancellation.
So what are the 3 cases then? Positive, 0, and negative?
Yeah, that's right. So the student question was like, what are the 3 cases? And the answer is lambda could be negative, 0, or positive. And each one of those 3 cases will give an equation of a different character that has a different solution. And I want to get into it just by like taking lambda equals 0 and analyzing what we get. So r squared hk double prime plus r hk prime plus now, or rather minus now, k squared hk equals 0. And so if you're following along in the book or reading along in the book, you know, they'll make this remark that since this is a scale invariant equation, the answer has to have a particular form. So I want to explain that remark. So first of all, an annoying fact about ODE is when you've got an equation equal to 0, that's called homogeneous equation, but homogeneous is an overloaded word. It has another meaning too. Homogeneous also means scale invariant. So this is a homogeneous ODE that's also homogeneous in the sense of being scale invariant. So I'll use the word scale invariant to describe this. So what do I mean by scale invariant? So my intuitive thought is, well, look, r has units of distance, right? So r squared has units of distance squared. So if I scale r by a constant, this will scale by the square of that constant. What about hk double prime? So assuming that, you know, h could have whatever units it does, but assuming for this argument, say that h is unitless, its derivative, what's the derivative? It's a limit of difference quotients, right? So on the bottom of that difference quotient is a unit of distance. So h double prime scales like 1 over distance squared. You're multiplying it by something that scales by distance squared, they cancel out. So changing coordinates by scaling does not affect this equation for that reason. Similarly, you've got one derivative scaling 1 over distance times one constant scaling by distance, they cancel. Here, there's no scaling. You just change the variable and the function changes. No problem. So you're left with whatever the units of h are throughout. If lambda were not 0, that gets messed up because now you've got something that scales like distance squared, nothing to cancel it out. So that's why this simplifies in that case. Now, what I explained to you is very intuitive, but what I want to not just be intuitive, I want to actually show you what's going on. And it goes back to this coordinate change business. So I'll come upon it honestly. So let's actually do a coordinate change. So let us do something like S equals R over C. So I'm scaling R by constant 1 over C. So this is the classical way to write a coordinate change. Certainly it's differentiable with an invertible with a derivative that's invertible, non-zero derivative. The sort of more formal way to write this coordinate change is to say, like, let's take the change from R coordinates to S coordinates, call it G of R, and that's R over C. So that's what we're calling S. So this function is the coordinate change. How should you conceptualize this? Well, if C is bigger than 1, then what happens? So think of C as like 100. So then as R shifts 100 units, S only shifts by 1 unit. So I think of that as like zooming out. You look at the map and you zoom out a long way, and a long distance becomes a short distance. You've now got this parameter, you know. Whereas if C is positive but less than 0, that's kind of like zooming in. So what happens under this coordinate change, the classical way of writing is, and you've seen this in the book, so let's call capital HK of S the function HK in the new coordinates, and that's going to be the same as little hk of R. And how does this work out? Well, if we note that R equals C times S, this is the same thing as HK of CS, which is now the same thing as little hk composed with G inverse of S. So this is the classical way of writing the coordinate change. This is the mathematician's way of writing the coordinate change. Take your function and let the coordinate change go from S coordinate to R coordinate. So G goes from R to S, G inverse goes from S to R. And that's the official relationship between these two things. So like when you see your book writing this, if you want to be formal, it's like actually that. On the other hand, this tells you that a small increment of S is like a small increment of R over a constant. This tells you now that D over ds, so like now with you've got the increment on the bottom, that's going to be D over dr times C, right? Because 1 over increment of S is like C over increment of R. You can also get this directly from the chain rule if you like that. So maybe running a little bit short on time, but if you want to rewrite this equation in terms of S, so this is just like we rewrote Laplacian in terms of R theta. We got a completely different equation. You rewrite this in terms of S, then what you get is that, again, R squared becomes C squared times S. And I'm looking at D squared over ds, HK of R. HK of R is capital HK of S. So just let me put that in there. And then, sorry, this was 2 derivatives, so that's D squared over dr squared, and then HK of R, which becomes capital HK of S. D squared over dr squared now becomes 1 over C squared, dds squared. So this becomes 1 over C squared. That's how it works out. There's the cancellation I was talking about intuitively. And then for r equals s times c, get cs, take the derivative with respect to r, that's 1 over c, derivative with respect to s. And then again, hk of r is capital Hk of s. And then you're just subtracting k squared times capital Hk of s and setting that equal to 0. And so do these cancellations. And do this cancellation. S squared, of course. Yeah, thank you. The comment was that it should be s squared. Absolutely right. And so look, you get the same equation. Of course, written in the new coordinates, but the same linear operator that HK, capital HK is plugged into. And so this is literally what is meant when you say that an equation is scale invariant. So that's sort of like what goes on in the mathematician's head when you say the equation is scale invariant. And so like the way that you would solve that, there's an ansatz or a general form that for a homogeneous equation, you want a homogeneous polynomial. Homogeneous polynomial of 2 variables would look like, if you take f of tx, f ty, that'd be equal to tn fxy. This is like a homogeneous polynomial of degree n for 2 variables. You've got a scale invariant or homogeneous equation in 1 variable, so you're expecting a polynomial that's homogeneous in 1 variable to be the solution. So this is kind of like a general method. Why would that be a good ansatz for your solution? Because you're taking away 2 derivatives, so you're getting like -2, and then you're bringing it back. So the same way that you used like e to the t or like e to the kt to do this Euler trick to solve constant coefficient equations. Here, for this particular kind of non-constant coefficient, that's a really good framework or ansatz, because what's taken away from the derivative is given back to you. Sort of like another way of saying that it's scale invariant, yeah. So you can kind of just plug this in. And I mean, that's a calculation that's not too hard. So since we are short on time, I'll just tell you the answer for what you get when you plug that in. So you seek an alpha that solves that equation, that solves this equation. So simply plugging in R alpha for HK of R and seeing what you get. Like alpha is going to have to depend on K. And in fact, the equation that you do get is alpha squared minus K squared equals 0. So telling you that alpha has to be plus or minus K. And so whenever K is not equal to 0, you get these 2 independent solutions, namely R to the K and R to the minus K. If K equals 0, you certainly get R to the 0 equals 1. And because it's second order ODE, there must be another linearly independent solution. You set K equals 0 in this equation, like bring that to the other side. This one I'll just, I mean, you can solve this with ODE methods, but I'll just tell you the answer. Like in this case, natural log of R solves it. Check that out. Like derivative of natural log of R is like 1 over R. So R over R gives you 1, and then derivative natural log twice gives you negative 1 over R squared times R squared gives you negative 1. They cancel each other out to give you 0. So these are like your 2 independent solutions. So now we've solved this equation for lambda equals 0 and K being an integer that could be 0 or it could be something else. So this this finds for us the value of HK in that particular case. And then the question is, like, can we solve this for lambda bigger than 0, can we solve this for lambda less than 0? And that's where the Bessel functions come in. They're not, you know, if you just say like the Bessel function like is a solution to this equation, then it's not so bad. You know, deriving that from first principles does take some time. So we'll actually finish this up at the beginning of next time, and then put it together, find the vibrational frequencies of the drumhead, and then solve the wave equation in 2 space derivatives. So I hate to stop right in the middle like that, but I thought it good to go into some more detail on some of these other issues. So thank you everybody for your time and attention. Thank you, Bill. It's great to see you as always, and take care.